Let's take a look at another subject matter here, and that's the situation of preparing a hairspring to go on the balance staff of a watch. Selecting the length of the balance spring is one subject matter. The length has to be correct for the beat rate to be in order. But the thing that we're going to look at here is the hairspring, and as we would prepare this to go through the regulator curb pins and also to go into the anchor pin. And let's assume for the time being that this is approximately alarm clock situation where we have to extend the outer coil in the regulator curb pin area, and that we have to set a little dogleg offset for it to be set into the outside end anchor. And let's see how that we would do that. And we have a couple of tweezers here that we looked at earlier, several hairsprings, and let's see what we can do with a couple of these. I haven't tried this before the camera previously, so I don't know how I'm going to be able to keep my hands out of the camera and take care of this. But let's just give it a whirl and see what happens. If I cut off one of these lights, I get a picture that looks like that. If I cut off another light, I get a, well, the light was already off. There seems to be very little difference there. And let's try still another condition. I don't know which of these will be the best in the ultimate picture, but let's just give this a try. Let's prepare the offset in the tip end of the spring. Here is the tip end that I'm holding in the tweezer. Let's prepare the offset in that end of the spring first. And if I may draw on this piece of paper, and we'll say the spring comes around something like this, and we'll set an offset like that. And in this region right here, let's say that the regulator curb pins are about there. From about here around, we will increase that radius. So this is the type of thing that we'll be doing on this spring. The first place is, how do you hold a spring? Well, and I'm going to have trouble picking this up, because what I usually do is stick a brooch through the hole in the spring, slide it off the table onto the ball of my finger, and then slip it down the brooch. And being that will get out of the camera, let's just see if I can do this type of situation. Set this on the brooch. One of the things we need to do right up front, and you always have trouble with these things jittering, so if you just touch it down to the bench slightly, you can suppress some of that jitter. We'll roll this brooch to see that the spring is indeed in flat with a collet, and this one is. We're okay there. If we want to pull this spring back and take a look, we can see what it would look like if we extend it a bit. So let's lay the spring on the table, and my collet is tighter than I had thought there, and I have the outer turn of this going counterclockwise, much as I have this picture drawn. Now, the thing I will do is form this outer offset first. The first thing I want to do is to form the inner bend, and let's call the inner bend about there, and let me get the tool that I'm going to use to do this. This little tool was made as an apprentice watchmaker many years ago. This was made out of 1/8 inch hard bronze stock. This has a slip clamp on it here, a split chuck in the end, and this is a sewing needle. And I've been using that a long time. Now let's see how this works. We just catch this with the tweezer right where we want the inner bend to be. We take this needle and we carry that back like that. All right, we go over the distance that we're looking for, and let's assume that distance is about there, and we take the needle and see if I can get my hands out of the way there, and we come back in like this. Okay, let's pick up and look and see if we got off flat. And indeed we did, just a little bit, and we can hold this up close here and give this a little twist. Not quite enough. Let's do it again. Give it a little twist there, and there we go. That's all there is to that. Get our needle back in hand. Now let's ask the question, suppose we decide this offset is too great. We can moderate that offset by opening this angle out right here and closing and opening this angle out back here. Now what that's done is has brought this section in a little bit closer, and that has to be looked at empirically. If you have the plate, that this is to go on, you drop this over the pivot and look at that in the position of the plate, and there you are. All right, let's look at the second situation, and that is pulling this turn outward right in here. We might ask, what's the little white square of paper for? Well, when I work hairsprings, I usually work on a piece of black paper. Black paper. Some kind of poster paper. Craft paper, whatever, not craft paper, some kind of craft project paper. And I cut a little square of white and put on top of it. And I work on the white square of paper. This is orange here. The reason being that I can have an intense light on the white without reflecting so much white all over this area that it closes up the iris of my eye. And generally when I work this, I use, if I'm not on the camera, even a smaller piece of paper than this. All right, let's move this outer turn out. Let's assume that it's going to be about a half turn back here, and we just go back here and catch this spring and do this. Well, I had my finger in the camera. Let's see if I can get it from here. Here we go. Now let's come over here, and I'll put the tweezer in my left hand. I don't work left-handed quite as well as I do right-handed, but I don't do too bad with it. And we do that. And right here, can you see I'm a little bit off flat in the end of that. Okay, let's catch this right here with a strong tweezer and just push down on that a little. There we go. We're okay now. Now let's look at our spring. Let's turn this around as you might look at this in a clock. And what's the problem we have? Do you pick up the identity of the problem at this point? When we move this curve out, we did not increase its radius. We just moved it out. So we need to pull that outward. And we'll do this. We don't want to go too far because we have trouble getting back. And I've hooked under the edge of the paper, and it'll take this a few tries here and see how we're doing. Went too far that time. There we go. Now we have increased that that outer radius, maybe just a little bit too much right in this area. But you see how easy this is to accomplish. Let's turn it over. Look at it again. Now that's how you get there with the setting up the end of the hairspring. Let's look at this on the brooch again and see how we look on. See if we're okay in the flat. And yes, we are. Yes, we are. We see if we can get where we can get this into the camera view. Now that spring would be ready to place onto the balance and set into use. You say, well, that looks easy. It is. It is. How long does it take to learn to do that? Well, been working on it for 40 or 50 years. But here's what I would suggest to the young clockmaker. This sack of hairsprings here, and they're pretty much tangled up in there, but they're all untangleable. That's about, seems like this is about 3 dozen hairsprings, and it seems like they cost about $3 from Supply House. And by the time you use up those springs, you'll know how you'll be able to handle this. And it's really easy to do, and that's how it is done. I had really intended, we'll just drop these all back in the sack here. I'm not contributing anything to untangling any of these. Putting these back into the sack, but don't worry about that when I use another one. I had intended to discuss some spring problems. You can shake these out and they'll all go down flat, and something like that, and you're back in good shape. I intended to discuss some spring problems and how do we learn to straighten a tangled hairspring? How do we learn to straighten a tangled hairspring? I guess I'll go back to the bag here and get one out. Have to have an example here. Let's go in here, and I don't know if I can find the one that we formed the end on or not. There we go, we found a different one. How do we get one untangled if we get one piece, if we get an end looped inside somewhere along the way? Well, we go back to the brooch again. I suppose that the clockmaker's brooch has more use for holding something than it does reaming something. Let's look at this. I noticed this spring, this is not the one that we had there just previously. It's a little bit off in flat. And we would correct that while it's on the brooch. Just reach back here and push on the first turn. Push on the first turn off the collet. And we can bring it right back into flat. Here's what you would do if you're tangled up. Slip this on the brooch, take the needle, go inside like this, and you start turning the spring. And you turn it round and round and round and round and round. See the needle following out, and when the needle gets to the outside, it's untangled. That's all there is to it. Now if you have a watch that has a hairspring stud on it along the way, that's a little more difficult problem. What I usually do with that, take a piece of pith wood, select a brooch that stick out a little further, stick that in pith wood, stick this, reach in here somewhere and stick this in it, stick both of them in the pith wood and start turning. Go round and round. Let's get out of the drawing here. Go round and round, and we get to the point we can't go any further. Remember, these two pins are stuck into the pith wood. Then take your hairspring tweezer and slip this stud back through the appropriate loop and continue on until you've got it straight. So that's how you untangle one. Untangling is not all that big a deal. Let's talk about some more on springs and some functions of a spring. Let me find a suitable tool here. You'd think in all these pliers that we looked at a few minutes ago that I wouldn't have trouble finding an appropriate plier, but I really wanted this little strong plier right here to hold a piece of spring. How about that? Well, let me turn that over by its shape. Let me look at this. Let's call this a piece of hairspring or piece of metallic stock or whatever that we're going to make something out of. Let's just say it's a spring. And let's take a pencil and mark somewhere along here a spot on the paper and see if we can get our spring over that. Now let's do this. Let's pull that spring this far and turn it loose and see what happens. It goes back to the mark. And we pull it this far and it'll do the same thing again and again and again. But somewhere, if I pull this spring far enough, it will not return. Now what we are talking about here, we are operating within the elastic limit. The elastic limit of the spring. In the elastic limit of the spring, it will always return to the original position, as long as we're in the elastic limit. If we exceed the elastic limit, as let's try exceeding the elastic limit down here somewhere, see what it takes around this corner. You see, we did not return. The old watchmakers and clockmakers say the spring is set. S-E-T, set. That is, it's in a position that it will not return. We exceeded the elastic limit, and that is the point of no return. If we go beyond the we exceed the elastic limit, and we have the point of no return, and the spring is deformed. If we go further, what did we do then? We reached the point of fracture. We reached the point of fracture. I broke the end off of the spring. This is the end right here. The spring was fractured. So we have three conditions that we can have. We can be within the elastic limit, the spring returns. We can exceed the elastic limit and deform the spring, or we can go to the fracture point and it's broken into two pieces. And take a look at the spring. This spring is, as one would come from the manufacturer, it is approximately to length, but not perfect. And the thing that we need to do is to find the pinning point and the regulator curb pin position on the spring. We need to raise the outer coil in the area of the regulator curb pin and form the offset in the end of the spring where it will be pinned to the frame of the movement. Let's look on this piece of paper and see what we'll do a little drawing here to see about what we think this would look like. If this spring develops in this order, and when it makes its last turn around, we need to come out to a wider distance. The regulator curb pin will be somewhere in this immediate area. We will continue on over here and get an offset where this will be pinned into the frame of the movement. Now, we want to locate this point on the spring. We want to locate this point out here and form this area of the spring, and then we want to begin at about this region to increase the radius in this area to match the radius of the travel of the curb pins of the regulator. So the first thing we'll do is place this spring on the balance staff. To do that, we'll use a bench block, and we'll select a hole in the bench block that will just accommodate the staff plus the roller pin, which is right there. We'll set the spring in place, and for this purpose and what we're doing here, we can place the spring on without regard to where its outer terminal will be located, and also without regard to which way that the spring develops, that is clockwise or counterclockwise, because we're finding the length of the spring. We will have it on and off of the staff again, so whether we have it backward or correct at this point is immaterial to this part of the work. We now have the spring in place on the staff. I was driving this in place with a little overshot punch. This punch has a hole that will just slip over that staff and drive the collet in place. All right, we have this assembled, and we'll go through the process of what is known as vibrating the hairspring. The tool that I have here is an English watchmaker's turns. That's a form of a dead center lathe. This is thought to be about 300 years old. This section here is where it was held in the workman's vise. The hook on the end is the place to hang the bow, which it was powered with. I have removed the tool rest from the central section for this particular job here. Let's set this wheel in place with the spring to my right. The reason I'm placing the spring to my right is because that I'm right-handed, and that's the easiest way for me to handle this parcel of work. It is necessary in this operation that the female cup centers that we have here have a slightly greater angle than the angle that's on the pivot. We want these pivots to touch down on their points, not on the conical portion of the pivot. The purpose there is so that the friction is a minimum amount, and that we do not inhibit the operation of the balance wheel. If we take a look, we see that this wheel spins very, very freely, and this is indicative that we are on the tips of the pivots, and we have the situation now that we can begin to look into finding the curb pin position and the anchor point on the balance wheel, or on the hairspring. This particular movement is 1440 beat movement, which is 4 beats per second, And what we're to do is to find a point that we can hold this spring that will produce that 1440 beats, 1440 beat count, or 4 beats per second. A beat being a change of direction. It is clockwise, counterclockwise, that represents 2 beats. Now, I'm using the what we might call the tailstock of the dead center lathe here as a rest. I'll rest my tweezer on that. Reach out here and I'll hold this spring with the tweezer, and I want to be very careful that I do not locate that spring off center or off flat or in any way tip it. We want this to be typical of how it would run in the movement. That is such as we have here, and I let that slip out of the tweezer then. Let's try again. Here we go, and we find that this is vibrating or oscillating as it would in the movement when it's operating. We find that it takes quite a number of cycles of oscillation for this to ring down to a stop. So we know that this is quite representative of how it would be running in the movement. Now, the question is, how do I measure a second, and how do I count 4 beats in a second, and how do I know when I'm right or wrong? That is not an easy situation to do. Many of the text on watchmaking and hairspring vibrating will tell you to count this for a half a minute, or better still, count for a minute, and these types of things. And counting absolute numbers and over a long period of time, this can be a very time-consuming situation. The thing that I do here, I have the shop regulator hanging on the wall here. As a matter of fact, I have 3 large regulators here in the shop. But there's one that is directly behind the camera that I can see the pendulum and also hear the beat. And I will concentrate on holding this spring and hold it with the tweezer rested, and such that the spring is not cupped, it is not off center, it's not stressed any more than it would be in the normal operating movement. I'm holding with a very fine point tweezer, and being cautious that the tweezer must not touch the adjacent turn. Everything is to be representative of running in the movement. And then we'll wind up, and at a particular tick on the regulator we will release this, and I'm going to count alternate directions of movement, so that I will count twice per second rather than 4 times per second. This facilitates the ease of counting. I will only count to the number 2. I'll count 1, 2, 1, 2, 1, 2, etc. And if I begin my count at the beat of the regulator that I'm observing, then after not many counts I can tell whether or not my wheel is either gaining or losing count. I don't have to be an entire count off, but I can tell whether it is gaining or losing without counting to a very high number of oscillations. So this is the thing that we'll do here. Now, it may help if you're not adept to this. I usually don't do this, but if we take a colored pencil of some type and give us a little mark on this. This mark is blue. You can use blue or black, I don't know. This is a lacquer permanent marker pen. Possibly we can see this in the camera right at this point. I believe we can. I can see it just faintly in the TV monitor here, but that may help. I simply just watch the spokes of the wheel for the reversal of the direction. So let's try, and we're not certain at this time that this spring is even workable in the clock. So the first thing I'm going to do is to catch the very outer tip of the spring and be of a certainty that the count is too slow. That tells me that the spring is certainly adequate in length to be used. If I cannot get too slow at the very extreme tip of the spring, then that spring is not usable with this particular balance wheel. So let's try that situation first. I'll have to take a hold of the spring. Let me get my hand a little more comfortably rested, comfortable here, so that I can hold this position for a sustained period of time. We wind up. I'll look at the regulator pendulum and let it go and count 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, and I'm indeed going too slow. Not very much, but just a bit. Now remember that probably the best thing that we can come out of this entire test that we're doing here is probably in the order of 15 or 30 minutes per day of regulation. Continuing, let's turn this around, and here is the tip of the spring. Let's bring around about a half turn, and this is shortening the spring about 1/2 turn, and let's try again. Let's see, this is oscillating faster now. The hairspring is shorter. I need to look very carefully and see that the spring has no two turns touching. I am not bumping the tweezer, and we'll wind up here and let go. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. I am going faster. I can detect that I am going faster than 2 per second. Now, the thing we conclude there, and let's slip the wheel out and take a look. The thing I conclude there, that if I hook up to this spring here, let's see if we can get in a position to see the spring. Lost the end there. Here it is. If I hook up its spring right on the end, where I have the tweezer at this point in time, I'm going too slow. If I hook up a half turn back, which is about here, and let's look, right here is the tip end of the spring. If I hook up about there, I'm going too fast. So we will assume that the regulator point, that is the point of the curb pins, should be somewhere in this region, right about here, right about there, somewhere in this region. So it appears that the length of that spring is approximately right for the particular balance wheel. So we'll remove this, and we'll set the anchor point. We'll set the offset for the anchor point out here on the tip end. We'll back off here about a half a turn, increase the radius on the outer section of that spring, and see how that particular work is done. All right. The question is, why am I using a little white piece of paper here? Generally, when I'm working without the camera being on the job, I work on a black sheet of paper like this. This is a kind of a soft black looking sheet of paper, and with the spring on wheel on top of that, and under an intense light. This will permit me to see the wheel quite well, but limits the reflection. I'm touching the focus on the camera now, but it limits the reflection of this surrounding area so that it does not close the iris of my eye. All right, let's take this spring off. You can see what it looks like if we lift the wheel by the spring. Let's remove the spring and we'll form the ends on it. All right. The simplest method I know of removing a spring, this is a little piece of about 1/4 inch thick acrylic plastic. I take the tweezer, slip up on the balance staff, right against the collet, and push down like that. And you just snap that hairspring right off of the balance staff. I believe that on our orange paper that we had previously that we can see this a little better. All right. Now, our next step will be to form this outer coil outward, the radius out there, and set the offset here. I'll have to pick up my needle tool for that, and looks as if I've misplaced my needle tool. Let me turn the camera off and I'll locate the tool. Returning, let's do a little thinking here about this. Right here, right there is the end of the spring. If we make this offset, we come up where we're going to pin it in the frame about there. See if we can turn this around and take a look. Here's the end of the spring. Let's say here's where the offset's going to be. This is about what will occupy the offset, right in between here. And then we cross here about 180 degrees, and it says that we need to begin our offset, our larger radius on the spring, right about there. So let's work at that point. Okay, we'll come down here and take a hold of this spring with the tweezer, and let me try my light and see if I can do better with or without the light. I don't know. And we'll try the focus. Looks like I just can't do much better there. All right. We'll lay this down, take the needle tool, and we slip right here. I'm holding the needle tool in my left hand, the tweezer in my right hand, and we will raise that turn out just a bit. Now what we're doing, we are holding this and moving the spring beyond its elastic limit so that it will remain in that position. Now looking here, we find that indeed we did go out, but we're in too close here, so we have to increase this radius out in this region. So let's try that, and we catch here and move out in a couple of steps like that. Let's take one more here at about here, not quite that far, somewhere along there. Now, and I think we overdid that a little along here. Now let's move outward to get our offset. We moved out to get the offset, and let's come back in again. Here we are. Now, taking a look, this paper is a little soft. It's several layers of paper deep. Note this. The end of this spring is up, just a little bit up right there. We're off flat. Let's turn it over and look at it. Being this paper is soft, a simple way to do this is just hold down here and press on this. Just embed this into the paper ever so slightly. That will form the end of that spring upward. Let's look and see how it how this appears now. And if we look at it, we are quite flat. If we had gotten off flat somewhere back in this region, we'd have to give it similar treatment there. But this sets our spring now correct and ready to place on the balance and to be used. Now let's see, where does it go on the balance. In the movement that this is used on, the lever and the roller pin, impulse pin, I suppose the proper term is impulse pin in this particular item, particular balance. It is here, and that's on movement front side. That means that as I face the movement, this is toward me. The regulator on this particular movement is on back side, so it says that the hairspring must go to the rear. The hairspring goes on the rear side of the wheel. Also, the angle at which the lever is in the movement is approximately like this, about 12 or 15 degrees down from the horizontal. As I face the movement from my side here, the lever would be about 15 degrees downward this way. The anchor point, the pin anchor, is over approximately here on the rear frame. That means that when I set this up, I'm going to need the tip of that spring to be, and this is per chance, not too far from where this dark mark is, right here. Here's the pin down at this angle, and the anchor point is going to be about there. So if we set the spring on the wheel with its tip approximately in that position, we will be correct. Let's find a suitable hole in the bench block to use for this. And remember now that we said that here is the pin, and right about here is the end of the spring. The anchor point is there, and the spring, the regulator is to the upper. This is the upper part of the balance wheel, so the spring must develop like this. Now, when we place the spring in place, the spring must go on like that. Spring must go on, it's starting in the center, winds clockwise, and ends up over about here. Okay? Let's put that in place. We take the overshot punch, no hole in that end of it. We go right here and we gently tap this down with a little brass hammer. Tap, tap. This is a pretty large bench block for this type of work, but it is not quite heavy enough. I'm sitting on this paper that's a little bit resilient underneath. Now let's take a look. We lift this off, and let's look to see if this spring is true and flat. And it looks like I need to touch it ever so slightly right in this region. What we do, we adjust it by forming it by pressing in the appropriate place on the innermost coil of the spring. All right, we're in good condition there. Now, how do we adjust the location of the tip of this spring if we've missed it? And we have missed it by, I would guess, almost 1/8 of an inch. I think we're almost 1/8 of an inch off at that particular point. Let me turn off the camera and I'll get the appropriate tool and we'll adjust the end of that. What's the appropriate tool? Well, appropriate tool is a large watchmaker's screwdriver. We just slip in this collet, and that collet is pretty tight, and we move this just a bit. When we slip the screwdriver in that collet and attempt to turn it as if it is a screwdriver slot in that split collet, it slightly relieves the pressure on the staff and permits us to rotate it, and we have the tip of the spring in position. When this goes into the movement, we will have to make a finer adjustment on that at the time it's assembled into the movement. Now, let's pull this out and try back in the test fixture here. We go back to the turns, and we'll hook up and look at this situation again. Be sure that we're completely free. Be very sure that we're completely free, and we are. The wheel spins for a long period of time. And this time, when we grab the spring, we want to hook on to the position of the spring that approximates what we had in our first sketch here, that approximates where we thought the curb pin would be. Now, when we're making the count, we will need to catch, to be comparable to the curb pin in the center position of the regulator, we need to catch the spring a little closer to its anchored end, because remember, there is slight breathing space in the curb pins here, and the dynamic length of the spring does not end there, but somewhere a little bit beyond in the slow direction. So if we catch this spring, here's the anchor point. Let's carry it down a little further so that I can catch from my rest right about here. And be sure that the turns do not touch each other or touch the screwdriver. And here we go. And let's start again. It's 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And that's the thing that we're looking for. Now, let's discuss escapement problems a little. This will not keep time unless the remainder of the escapement is in order. If we have escapement errors other than the hairspring itself, they may overshadow our judgment on the hairspring and may even carry the rate into error. So as we assemble this into the movement, we need to be very sure that our pivots are very clean, very good condition, the jewels are in good order. We have to be equally sure when we have it in this fixture that the pivots here are equally in order. We have to be certain that everything is in order, because it's entirely possible and pretty highly probable that there would be escapement problems that would influence the rate, that would overshadow what the hairspring would call for the rate to be. Now, this is how that we find the way. I would generally assume that we ought to be in this and within 15 or 30 minutes per day of being correct on the location of the spring. That's about what this type of work will give you. And the regulator in most of these, in this class of clock, does have about plus or minus 15 minutes a day in the range of the regulator. When we set this into operation, we can observe this in just a very few minutes or a very few hours and see about what the range is, and then move the regulator and see if we can come into range. If we can, if we are approaching the end limits of the regulator, observe the regulator itself to see about how much change we need to make in the spring. In this particular IBM master clock movement, it's an automatic regulated movement, and things come a lot easier than it does in just a free-running movement. This particular movement drives into a differential gear, system of gears that has an input into that differential from a synchronous motor and from the spring-driven escapement that we have here. And the output of that differential gear system then is returned to the regulator. So it says that the escapement rate in the IBM movement, the escapement rate is compared to a synchronous motor electric motor rate. And the error is returned to the regulator. And this movement will regulate to absolutely being on rate within about 10 minutes after the movement is set into operation. Within 2 or 3 minutes, you can see the direction that the regulator is beginning to move and recognize whether or not you are, whether your hairspring is on time or not, whether you need to lengthen or shorten the spring. So in that particular movement, it becomes very easy to do this type of work. I suppose that I have done hundreds and hundreds and hundreds of these over a period of many years as I worked in the service organization of IBM, and I find that in grabbing one of these springs and counting the time, that I have a high degree of confidence in the count and the result I get. I find that what I learned in working with that type of movement directly assists me in any form of movement that uses a balance wheel hairspring system as its oscillator. I find that that helped me in watch work, it helped me in clock work, it helped me in all types of devices in that. And having done so many of these springs, when the IBM movement, when the springs come from the factory supply, we got bulk springs, we got bulk balance wheels. When I say bulk, I mean wheels without springs and springs without wheels. And any time that a new spring went on a wheel, it had to be vibrated. There is minute differences in the dynamic characteristics of the wheel, and the springs are not interchangeable from wheel to wheel, just as it is in a clock that we would be repairing today, or just as it is in a watch. But the ordeal, to many clockmakers, to many watchmakers, it's only been through this a few times, the ordeal seems to be almost an impossible task. But I can assure you that each time you do it, it becomes easier and easier and easier. And I personally only consider it as just another repair in the course of events of a day. So this is how that we get a balance wheel and a hairspring in order. Dealing in a watch, the principles are the same. Of course, all the dimensions are smaller. It's more possibly more tedious to handle, depending upon your individual dexterity. But with modern-day watch timing machines, it's still not all that big a situation. So that's the way it is on the JB Ranch, and assembling a balance wheel and a hairspring. And good to have you viewing this action. I'm J.M. Huckabee, and this is January the 13th, 1988. Continuing on hairspring problems, these springs here were purchased as a bulk quantity, and oftentimes we find that colleted hairsprings that we cannot, though we have a spring that is suitable in strength, length, etc., that the hole in the collet is improper. And oftentimes we may need to reuse a collet or make a hairspring collet. we find we generally handle these springs by slipping them onto a tapered brooch so that we can hold them in our hand for inspection and whatnot. But suppose that we're in a position that we just very badly need to transfer a collet from one spring to another, or that we simply have to make a collet from scratch. So let's go through. The size of the work is so small that I can't very well show it on the camera here, but let's go through the thought process of making a collet or transferring a collet from one spring to another. We'll find that it really isn't a big ordeal at all. Let's move over on the edge of the paper here where I can sketch a little bit, and let's say, what does a collet look like? A hairspring collet, if we draw it, would look something like this, with the slot in it, and its hole like this. The hole is in the center of the collet, of course, and we have a little undercut in the central region of this thing. You might envision it as looking somewhat like a V pulley. Let's turn it on edge and take a look and see what what this would look like. If we set the collet on edge, it would look like this. I should have drawn this in comparable diameter to that, but it would look like this. Here is the hole through the center of it. Here is the slot. That slot is down here now, and this is a groove in the edge of this. Now the hairspring lies in this region right in here in the collet. This is hairspring right in this region here. Now the spring, the edge of the collet, is crushed in right in this region onto the collet, onto the spring. Now let's imagine right here from this drawing that we developed the spring. That spring starts up in here somewhere, travels around, and makes a little more than a half turn, about 3/4 of a turn, and then exits. So here the spring exits, makes a sharp bend, and begins to make its development like this. Let's show the thickness of the spring. This is the thickness of the spring in the development, and this goes on to the outside end. This is spring through here. This is latched in place by a staking punch strike, let's say right about here on the blue part of the collet. We're going to stake right in this region, and what that will do is crush the edges of that collet in and close it on the spring. That's a classic way of fastening the spring in place. Let's move these springs away and get another place on the paper and look at this again. Here is the collet, the slot that's in it, the center hole, the depth of the groove that's around it. Let's turn this on edge and look at it, and it's like this. Looks like a little pulley, and the bore of it is through here somewhere. The spring is going to lie, again, it's going to lie in this region, and we're going to crush or roll over a pinch point on the edge let's say down here somewhere, to hold that spring in place. If we need to make a collet, if it's necessary for us to make a collet, we make this in the lathe, and we use this process. If this is the chuck of the lathe, we put our stock in here. This is the lathe chuck. We turn this off, true. We square this off, and we drill this region going up in here. We then turn the groove that's going to make the collet like this. While it's in the lathe, we take a saw and we slit this into the hollow. We take a cut-off tool and we cut this off and drop it into our hand. This never leaves the lathe stock until it's finished. We catch that on a broach. So making a collet, for a clock the size that we're talking about here is of no more consequence than making a bushing to go in the plate. Once you've made a few of these, you can make that collet in possibly 5 or 10 minutes. Shouldn't be over 10 minutes at the most. Now let's say, how do we handle that situation? How do we get the spring on it? We take our spring, and the development of the spring might look something like this, and our collet diameter may look like this. Much smaller. I noticed that my blue pen on these outer lines and my black pen here comes out the same color on the TV monitor. Here's the thing we do. Let's take the spring. Down in the central region, we form that spring, the curvature of the spring, a little bit smaller than the collet. Like unto this. Then we take the collet and we spread this, slip the collet into the spring. Now the collet would be over the spring, like this. Now the collet cannot fall out of the spring. We've put the piece of spring in it, and we've caught it in the eye in the center of the spring. Here's the collet. We take this to the watchmaker's staking set, take a little punch, and we crush it there on the edge. And that's all there is to it. If we have to change the collet from one to another, we may find that the collet structure is such that we can reuse it. Let's look at it from this standpoint. If the collet looks like this, and it has the crush mark here, where that the old spring exited somewhere around like this, we can break this off up close, slip this on a broach, much as I have this on a broach here. Set this, we've broken the old spring loose, set this on a female center in the lathe, this in the headstock, take a tool and cut out in our V-pulley groove, that groove that was in here. This groove that was in here, this would have been crushed over a bit. In here, the old spring in there. We have this on the broach, turning in the lathe, and we simply go in this slot and machine away this little bit here and flip that piece of spring out. Now, when we place the new spring in there, rather than attempting to stake it back in the same spot, we just move around and stake it in an adjacent position. So we find that if you're adept with a little bit of lathe work, and you need to change the collet from one spring to another, that it just isn't much of a problem. And we may find that the spring we will probably lose the equivalency of a half a turn of the inner part of the spring if we break one off and transfer a collet or whatnot. But remember that a half a turn at the collet only represents maybe a 1/16th of a turn at the outer end of the spring, and oftentimes this can be compensated for by pinning point or regulator position. So you see, if I have a spring that I need to use and the collet doesn't fit the staff that I have to use it on, I can transfer the old collet or make a new collet. I've never really been successful in chucking up a collet with a spring on it and going inside, boring a hole, and enlarging a hole. If the hole is too large, it's very feasible to make a little bushing to go in it. That isn't too much problem if the misfit is fairly great. If that bushing only needs to be 1 or 2 or 3/1000ths of an inch thick, it's difficult to handle that. But to open up a collet is not something that I would assume that you could do successfully. A good lathe chuck can grasp this, and the spring could run free in the air, and if it runs in the direction that the spring is being wound, it could shuck off the chips without any problem, and you could conceivably go into that with a boring bar with a tool slide rest and open that collet out and do it successfully. But the probability of doing it without making a mistake and tearing up a hairspring is somewhat remote. To me, rather than risk damage the spring, I would just make the new collet from a piece of brass. You want the brass to be free machining. It can be quite soft, and the machine work, the dimensional integrity of it doesn't have to be met in absolute terms. If the sizes are approximately correct, then you can work that out and fit it up to the staff all right. So that's what you would do in the event that you have spring problems and you can't adapt the collet that you have to the spring. You just simply change or make another. Now let's think in some other terms on a spring, and this is just some observations. This spring here is a steel spring, and it is quite stiff, and when you attempt to form this spring, as we did in some of the illustrations on this tape and the previous tape, you find that as you work it, you would call it a very stiff spring. If we look at one of this type, this spring appears to be made of a material that contains beryllium, and though there are various degrees of strength on it, this is a softer spring, forms easier, and generally would, all other dimensions being correct, you would generally come out with it being shorter for a given balance wheel than you would with a steel spring. These two are by no means interchangeable. This is for a much smaller balance wheel than this one. Here's another spring that looks like is a steel spring. Notice when I pick this up, this one's tangled. This one is tangled. This outer end has gotten looped back through the inner turns there at some point in time, and it says that it has to be straightened out before it can be used. I believe that on the previous tape we discussed how to get a tangle like that out of the spring, but just to show this again, it's not a particular problem. You take the slip it on a brooch, stick your needle tool in it and start turning it round and round and round. And we iron the tangle out of it. What we're doing where the intersection is, and we do this again. Let's just slip this tangle back in there. It looks like I'm having more trouble getting it tangled up than I did getting it untangled. There we are. We've got that end looped back in there and it's tangled now. All right, we go round and round and round, and there we've popped it out. And I believe I discussed on a previous tape, what do we do if this is in a watch and we have a stud on the end of the spring and we can't pop that out? How do we do that? You see, that stud on the end of that spring that gets through there has to be lifted through the turns. I like to stick this into a piece of pith wood and do it like this. I'm holding these two tools in the same hand here. I'm holding these in my left hand here. But you see, I can rotate. I'm holding the needle tool sticking into the paper, and here's another view of it. You can see I spin the brooch and come out. Here we can wind it back in. So what you do if you have that stud locked up in there, you spin this to the point that you've got the stud caught up where you can't handle it anymore. You take your other hand, you take your third hand. You learn to, we need to practice every day of our life with the wrong hand. See, I'm using the left hand here for this, and using it as two hands. We get to the point we can't handle the tangle, and then we reach down here with our right hand, and we very carefully lift the turn that has the stud on it, and we lift it out between the turns. See what I'm doing here with my fingers, how I can spread this spring apart? Having trouble here we go, in the perspective of the camera. And we can take the second hand, our number 2 hand, and catch the ends of it, and even if it has a stud on the end of the spring, we can fish it out from between the turns. So that's how you go about untangling it. That's not quite as simple as it might look here. You know, remember, I've been doing this for a long time, but you see how we can take the two tools, separate them very widely, roll this around, and if we had the stud hung up here, we can lift it out, turn at a time. This is the way you get 3 hands out of 2. We finish here, and in all this ordeal of twisting and turning, we don't have any problem with the spring. I have a group of these springs in an envelope, and they're all pretty much tangled up in here because they're not individually wrapped, but it's not a problem in straightening them out. Sometime when you have a few spare minutes and you want to do something to improve your dexterity, untangle an old hairspring. Maybe a little rough on your nerves the first few times you try it, but it's good for your dexterity. All right, let's end our hairspring discussions at this point. This is J.M. Huckabee at the JB Ranch. Continuing our study on the balance wheel of a clock, let's take a look in a simple little pin lever clock movement and see what the watchmaker sees through his eye loop. With the watchmaker in his eye loop, you see exactly what is on this picture right at this moment. Everything is out of focus. Everything is out of focus. And as we come into range on the eye loop, we find that we constantly tumble and search for the focal distance, the light reflections and ultimately find the area that we're to look at. And we find that essentially everything in the job that we're working on is out of focus except one small, tiny area that is important to us at the moment. We find that the uninitiated, I suppose I could say, that sees the watchmaker, they oftentimes think that the old duffer has the palsy. But in reality, if you notice, as I tumble this movement, the light reflections, we see different areas of it in the advantages of position and reflections of the light. The higher the magnification that we have, the more pronounced that situation will be. Let's look into this movement, and later on the film we'll look at the movement in its entirety. But if we look to see what this is the center shaft right here that carries the minute hand. The hour hand pipe is not on here at the time. This is the minute wheel. This is a one-day spring-driven movement, about 50 or more years old. It is, the mainspring is down at the moment. It's run the extent of the period of time that it can drive the movement. It's rather dusty, as it's one that I picked up about the shop here, just to use as an illustration. But let's look at some things that's important to the balance wheel movement running well. The first thing that we want to find out is that the clearance on the pivots is near zero. I'm attempting to shake this wheel. I've got a little bit of shake in this pivot here, but we should be essentially zero. We need to avoid becoming too tight, because as we wind this spring, we may rack the movement just a little bit, twist the plates on the pillars or whatnot, and we may go into a bind. And we must be sure that when we're fully wound, or that the stresses of winding doesn't carry this into a bind. We would say that this is pretty much nominal here. The picture you're looking at on the TV screen is several times as big as this balance wheel. This balance wheel is about 5/8 of an inch in diameter in the real world, maybe a little more than that, but less than 3/4. Let's look at the hairspring. Let's tumble and get the light reflections and concentrate on the hairspring and the hairspring only. As we look at this, we can see that it has some fragments of lint on it here and there. From the back side, from the camera side, which is behind me, we can see the lint on it here. We see the stud, which pins this the outer end of the spring into the frame, and the outermost coil begins somewhere down in this lower region, right in here, and is extended outward to a greater radius, and there it accommodates, or that's where the coil passes through the curb pin of the regulator. Let me find my pin here, the tip of my pin tool, and we see the spring breathing in the air gap of the regulator. See what's happening there in that regulator curb slot. The thing that we notice is that we're touching one side of the slot more than we are the other. If we would form that spring down in the stud area so that it would more approximately center and touch the two sides equally, it would give us a different rate for that position. There's another thing that you find, and that is as the movement runs down and the balance magnitude, I'm having trouble getting back there, the balance magnitude gets smaller, we find that the spring touches the curb for a less period of time. That means that the dynamic length of the spring increases as the magnitude of vibration diminishes, and it says that that will give it a slowing rate in the shorter arcs. If we look, I've got a problem here. I just dropped my needle tool on the floor, and I can't retrieve it readily. Let me try this brooch. It's a little bigger. Possibly we can see it a little better. As we look in here, this is the regulator out to this position. We come up the shank, and then here is the arm that we would actually regulate the rate of the movement. As we look at the hairspring, let's find a position that we can see the hairspring. We inspect the spring for it being true and flat. We inspect it for being true and round. That is, the development of the spring is approximately concentric about the axis. Let's see if we can turn this to the opposite side and see that. We want to see that the spacing from turn to turn spacing as we come out in that spring is consistent. We want to see that there's no kinks in it. Now let's notice this. Look down near the central axis of this spring, and you find that one of the turns, the first lead-off turn from the collet, is not quite symmetrical, and we see the central area of the spring with a little bit of looping action in there. If this were a fine clock or watch, we would have to correct that to take care of the rate problems that results from that. The spring is pinned into the frame anchor right here, and let's look at the aspects of the beat adjustment. We want the relationship of the lever, the pins, the impulse pin, the axis here, and down to the escape wheel. There's all a set of rules and circumstances that we need to observe there. But in the most primitive form, the axis of the escapement lever, which is, this is the arbor for the escapement lever, and the impulse pin. Let's see if we can get where we can see the impulse pin. The impulse pin, which is having trouble getting there. It's inside the fork, right in this region. Let's roll the wheel around where that we can see it. Here it is. And I'm just having real trouble getting my perspective right. Here it is. Here's the impulse pin on the wheel. All right. The staff, which we're looking at right here. The staff, the impulse pin, and the axis of the lever here. When there is no torque on the powertrain, these should line up in a line. And if we look at that, we would find that the axis of the balance wheel, the axis of the escapement lever, and then the pin on the balance wheel, these should line up in a straight line. Now, as we look a little further, let's see if we can find the escape wheel down in this inside here. We're looking in this region. Here's the escape wheel, and if we look at that escape wheel, we find that these teeth, that the tops of these teeth right here have an inclined plane on them. Inclined plane on the teeth there. One of the escapement lever pins in the pin pallet should be sitting on that inclined plane when we're sitting here at rest with no torque on the train. Now the object of that is that when the movement is wound, that it will be self-starting. It's entirely probable and quite often happens that the movement cannot have that condition and still run reasonably satisfactorily, but would not be self-starting. You want the movement to be self-starting. We can see the escape wheel turning right in here, and let's see if we can find the pallet pins on that. I saw the pins here a few minutes ago. Well, I can't get the pointer to the pallet pin. Let's see if we can see it right here. If you can see where the tip is on the escape wheel, we can see that condition. Now, if that condition exists, we can wind the movement, and it will begin running. Or I could just set a little torque on the train out here on one of the outer wheels, and we start into motion. Let's wind this movement up and see what it looks like when it's running. I imagine this will run 30, 40, 50 hours, something in that order, on a full wind. Let's wind it up and see what this balance wheel motion looks like under that condition. There's a black mark on the wheel here, and what we're seeing right at this point is that mark, see if I can get my perspective right, that mark is reaching from about there to about here. If I can get close and not touch, that mark is reaching from about there to about here. That says that this wheel is making one revolution plus that amount of distance. It's probably running in the order of 380, 390 degrees. Would that be correct? Yes, about 380, 390 degrees, something in that order that wheel is making at that point. Let's look at the hairspring and inspect that hairspring to see if in these long arcs, if we have two turns of it that touch together. And looking at it here, I don't believe that we do. The development of it is pretty good for a flat hairspring. If this were an overcoil type spring, it would be expanding more equally around its entire periphery, but the motion of it here looks good. Let's look at the pivots. Let's look at the motion of the movement with it lying. This would be dial down, and this would be dial up. There appears to be little or no difference in the friction in the two positions because the swing of the balance does not change. Looking at it in this position, well, let me find the way here a bit. trying to look at the flatness of the hairspring. There appears to be just ever so slight amount of error in the flatness of the spring. We're looking at this being the spring right below this. Looking around a little further. Let's find the curb slot on that regulator again and see what it looks like when we're making the longer arcs. There we go. I'm getting close to finding it, and I got my little finger on the wheel. We are still showing that we're against one side of the curb more than the other side. In a fine watch, we'd want that clearance on that regulator to be essentially zero against the spring. We would want that curb slot to be the dynamic length, or set the beginning or the ending, as the case might be, the outer end of the spring. Actually, the dynamic length of the spring is something beyond the curb point in this particular movement. We would ask the question, what is the value of this little movement? And I would have to tell you, not much. It appears at one time that it had an alarm mechanism back here in the back of it. I do not have the case for it, or the dial, or the hands, or anything. There are some numbers back here. Let's see if we can pick these numbers up and see what they say. Right here is a 12, and over here is something, and back in this region is. Let me turn it around and see if I can see that. Looks like it says 1244. I don't know whether that's a manufacturing date on that or not. This is Westclock's movement, identifiable by the cast pillars and the cast arbors. This is a lead alloy material that Westclock's used in their arbors and pillars for so many years. But as we look at this is the type of thing that you encounter in clock movements. Is it fine? No, it is not. But it is pretty typical of some of the things that you will find in the antique market. And you'd be surprised what a modern-day pilgrim would pay to have Grandma's old alarm clock repaired. So don't treat these things lightly. In the repair trade, they can bring you dollars, just like working on high-class clocks and watches. I don't know where I picked this up. It's been sitting around the shop for quite a number of years. Oftentimes someone come in, I use it as a conversation piece. But I thought that while we were looking at the hairspring balance wheel situation, we just look at one of them running here on the film. Let's look at it again in about this position. You say, well, is this film pretty typical, or this tape pretty typical of what things look like? Well, I can tell you, this is exactly what I see through the eye loop, all day long through the eye loop, because the eye loop has a very limited depth of field of view, and you depend very highly upon the reflections from the material for the tumbling, the angle of view, and whatnot. It takes a lot of practice to get so that you only look at what you need to look at and disregard all the other things. So this is, if you're a young clockmaker, young watchmaker, this is the way it looks through the eye loop. There's nothing magic in one of these glasses that would enlarge something 2, 3, 4, 5, 10, or 20 times. The greater the magnification, the shallower the depth of field, and the more things that are out of focus, and the less things you see. Now, while I'm doing this on the camera, see, I have a close-up loop on the camera, and I'm having to freehand hold this movement, and I cannot see the movement directly to any extent. I'm looking on the TV camera and attempting to point this out. I thought this would be an interesting thing to take a look at and see what a hairspring looks like in action here. Really now, does that really look any different from what we were doing in the English turns when we were locating the end of the spring? It's the same thing that we've been working on this tape. Well, pleased to have you with me. I'm J.M. Huckabee on the JB Ranch at